Last episode, you watched a gradient flow backward through the toy net, the seed 0.6398 at the output rippling back into every weight, landing on a gradient norm of 0.31. It felt almost too easy. One backward sweep and every parameter knew how to move. So, here's the question that should be nagging you. A real network has a million parameters, 10 billion in the big ones. How is it possible to get a gradient for every single one without doing a million separate calculations? Tonight we answer that. And the answer is the reason deep learning exists at all. Start with the naive picture because it's the one almost everyone draws in their head first. You've got a loss and you've got a million weights. To know how the loss responds to weight number 1, you nudge it a tiny bit and rerun the whole network. Then weight number 2, nudge, rerun. The misconception here is subtle and almost reasonable. A gradient is a million separate questions, so it must cost a million network runs. If that were true, training would be a million times slower than prediction, and nobody would ever train anything. Hold that number in your head, 1 million passes, because we're about to demolish it. That nudge and rerun idea has a real name, numerical differentiation, finite differences, and it genuinely works. It's how people sanity check gradients, but the cost is brutal, 1 forward pass per parameter. For our headline million parameter net, that's a million forward passes to get one gradient, for one training example, for one step. The myth people carry is that this is just how derivatives are computed on a computer. It isn't. It's the slowest possible way, and it's only ever used as a unit test, never in the training loop. Now meet the two honest modes of automatic differentiation, the real machinery. Both compute exact derivatives, no nudging. The difference is the direction you push information through the graph. Forward mode starts at the inputs and carries derivatives forward alongside the values. Reverse mode, Backprop, does the forward pass first to record values, then sweeps derivatives backward from the loss. Same graph, same exact answer at the end. The misconception is that these are interchangeable, that you'd pick whichever feels natural. You can't. For training, one of them is catastrophic and the other is the whole game. Here's the rule that decides it, and it's the most important sentence in this episode. Forward mode costs 1 pass per input you differentiate. Reverse mode costs 1 pass per output you differentiate. So the shape of your function chooses your mode. Forward mode is cheap when you have few inputs, many outputs. Reverse mode is cheap when you have many inputs, one output. Now look at training. A million weights as inputs and a single scalar loss as the output, one output. That is the most lopsided case imaginable. And it's exactly the case reverse mode was built for. Let's make it concrete with the carried through toy net so the numbers are real. 4 parameters in, 1 scalar loss out. Forward mode would push 4 separate derivative tracks through the graph, 1 per parameter, to fill in all 4 gradients. Reverse mode does 1 forward pass to compute the loss 0.2047, then 1 backward pass and outfall all 4 gradients at once. With norm 0.31, 4 to 1 becomes 2 to 4. The lopsidedness is the free lunch. Scale that intuition to the headline. A million parameters, 1 loss. Forward mode, roughly a million passes, 1 per parameter, because each pass only learns the sensitivity to 1 input. Reverse mode, 2 passes, period. 1 forward to record activations, 1 backward to harvest every gradient. 2. Not 2000, not 2 per layer, 2 total independent of how many parameters you have. That flat line is the single most important economic fact in deep learning. The cost of a gradient is the cost of a prediction plus 1. One honest caveat because I promised you the senior engineer version. Reverse mode isn't free in memory. To sweep backward, you have to remember the activations from the forward pass, the values at every node. That's the trade-off. Backprop spends memory to save time. Forward mode is the opposite, almost no memory, but a pass per input. So the myth that backprop is just obviously better needs an asterisk. It's better for this shape, many inputs, one output, and it pays for that win with the activation memory you'll learn to manage later when we hit checkpointing. So step back and feel the size of what just happened. The naive picture said a gradient costs a million predictions. The truth is, it costs one extra prediction. That factor, a million down to 2, isn't an optimization you tune. It's the structural reason you can train a network with billions of parameters on a laptop's worth of math per step. Every loss curve you'll ever watch go down is riding on this one fact. Let's go see it in code and put the two bars side by side. Open nnautodiff_cost.py. It's a cost model, not a training run. We're counting graph passes, not minutes. Top of the file defines the two functions we care about: a generic graph with n in inputs and n out outputs, and a tiny cost function that returns how many passes each autodiff mode needs. Then we plug in two scenarios, the 13 param toy net and the million param headline net, and print the verdict. First block, the cost rule itself. Forward mode passes just returns n in, one sweep per input. Reverse mode passes returns a constant 2 whenever there's a single scalar output. One forward to cache activations, one backward to propagate. Notice reverse mode ignores n in entirely. That's the whole point, and the code makes it literal. The input count never appears in the reverse formula. Second block, the toy net. We set n in 4, n and out over 1. The 4 parameters from OPO3's net and 1 loss. Forward mode reports 4 passes, reverse reports 2. We also assert the loss and grad norm constants 0.2047 and 0.31, so this file stays welded to the backprop episodes. If someone edits those, this script screams. Third block, the headline net. N indoor 1 around those and out over 1. Forward mode returns 1 million. Reverse mode returns 2. The formula didn't even look at the million. We compute the speed up ratio 1000,002 and get 500,000x. That ratio is the number to remember. Reverse mode is 500,000 times cheaper here, and the gap only widens as the net grows. Last block builds the figure data, 2 bars op counts on a log axis, because a linear axis can't show 1 and a million in the same frame. We label the magenta bar forward at 1e6 and the teal bar reverse at 2, and print the headline line the figure visualizes. No training, no randomness, just the arithmetic of the cost model, frozen and reproducible. So that's the free lunch, fully costed, one gradient for the price of one prediction, no matter the parameter count. But notice we did all of this for a single training example. One X, one loss. Real datasets have millions of examples, and you can't afford a full backward pass over all of them for every step. Next episode, Vanilla SGD, where we make the boldest gamble in optimization, estimate the gradient from one example at a time, and find out exactly how noisy that bet is.